Hello class, this video is going to help with 12.1, which is the start of our antiderivatives and integral section. So the rest of this year we're studying what we call an integral, which is just doing the antiderivative. So what if you have a function and it's in derivative form and you want to go back to that original function? Okay, so one thing that kind of throws us for a loop is that number at the end. We know when we take the derivative, any number goes to 0. So how would we go back and know what number that was? Well, we can't. So what we'll do is we're going to use this letter C for our constant. So we'll do the function the best we can, and we'll say plus C at the end. So on all of your homework problems, you have to do the plus C for an indefinite integral, okay? Indefinite. So if we looked at something like the derivative is equal to 6x squared, all right? So here's our derivative. How could we go back? Well, we know our derivative was to subtract 1. So we know we should add 1 to that exponent, okay? So that's our first thought, is to add 1. What else do? Is we bring that exponent down and times it. So when we go to do the antiderivative, what we're going to do is we're going to think, okay, we know this is going to be plus 1 more. And we have a 6 out front right now, but we would have had to have divided that by 3, or we would have times it by 3, so we have to undo it. So the whole idea is you add 1 and you divide by what you added, because that's would have been what you times by. So I add 1 to the exponent and divide by whatever that is. So then this is going to come out as 2x to the third plus c, because we don't know what number was there. And then double check, does this get us back to this derivative? So we would go 3 times 2 is the 6, minus the 1 is the square. So perfect. And then the whatever number would have dropped off. So this does get us back to our derivative. So let's write down this idea. So we use a new symbol, kind of looks like this. To me, it kind of looks like a fancy S. And this is an indefinite integral. And basically what an indefinite integral is like, now I lost my train of thought. Indefinite integral is like a formula, like you're getting out a formula. You don't get out a specific number. A definite integral will give us a number, like here's our answer. And we'll actually do a lot of those as well, so about half and half. But indefinite integral is used to represent finding that antiderivative. So this is the symbol for the antiderivative. So if we wrote down some notes, the first idea is if I have this integral of x to the n dx, this is like what I would see, okay? And what that is saying is this is the derivative, and I need to undo the derivative and make it the original function. And the way that this would work, how we would solve this, is the x is going to add 1, just like we did, and then you're going to divide by that added 1, then you're going to add the c. So that's like function, so how we're going to see it. We're going to see it like this, and we're going to go, okay, so to get rid of the integral sign, we're going to go back to original function, and we're going to do that by adding 1 to the exponent and dividing back by that. Okay, another one that we might see is e to the x dx. Okay, so right now we have e to the x dx. How do I take the antiderivative or the integral, same thing, of e to the x? Well, it's e to the x, so both ways, right? So this would become e to the x, and again, what do we have to add to it? plus C, because we don't know if there was a constant there or what the constant was. Okay, one more for today's lesson. And what if we have the integral of 1 over x dx? Well, if I brought up that as -1 and I added 1, I would get a 0. So you can't get a 0 exponent because that makes it go to 1. Anything to the 0 is 1. So if you have something that would give you that 0 exponent, what do you have to do? Is you have to do the natural log. And we have to use an absolute value in here, plus C, because we can't do the natural log of a negative. So it makes you include that absolute value on whatever is in that integral. I mean, in that natural log part. Okay. And x can't equal 0, which we should know from there. All right, so let's start to do some examples using these 3 ideas. All right, let me flip this paper over. So here's my first example. What if I have 10 dx? Well, that looks like an S this time. Where's that button that I found? Perfect. Looks a little blurry. I can get it to come in clear. There we go. So if we have just 10 dx, what's that going to equal? All right, it's just 10. What it's going to equal is 10, and then you add the x onto it, right, and divide by a 1 plus c. So if you have a number, it just becomes that number with an x. Just like with the derivative of this, it would become 10. Okay, and then you have your plus c. Okay, what's another one? What if I have x to the third dx? So pause the video, see if you can solve that one without my help. So we would subtract 1, or excuse me, add 1, and then divide by that one, and add my c. Done. Okay, so let's try to make them get a little harder here. What if I have 5x to the negative third dx? It always has to have the dx on it there for the integral. Okay, so so if we have this as our derivative here, then what would be our antiderivative? Well, I'm going to add 1, so it's going to become 5x to the negative 2 divided by negative 2 plus c. Okay, so again, add 1, that makes negative 2, keep the 5, and then divide. 1, 2, 3, 4. All right, what if I have a fraction? X to the 2/3 dx. So what would happen to the fraction? Still adding 1. Okay, so the fraction, it's going to become x to the 2/3 plus 1 is 5/3. You add another 3 on the top because 3 makes a whole. So we add 1 and then we divide by 5/3. So to divide by 5/3, you flip it and multiply so that it becomes 3/5. And then you have your x to the 5/3. And then what am I missing on this? Plus c. There we go. Okay, so those are the basics. Couple other rules or notes that we want to make sure we have is, this is like my 4th one here, is if I have a number times my function in here, dx, I can take that number out front and then just deal with what's inside. So basically, like up here, I could have taken this 5 out front. I could have then dealt with the x and then times it by 5, which is exactly the same thing as what we have. But that might be helpful that we could take the numbers out on some of them. Well, I know it's helpful. So there's one rule. One more rule I want to make sure I write down is the idea that if I have a function plus or minus another function, just like we have all the time, we have x to the third plus 4x and minus 3 or something like that. We know we can take the derivative of those by taking each part. Same with the antiderivative. We can then have the antiderivative of each part, plus or minus, whatever it is, to the next part as well. So that allows us to take the antiderivative of each section, just like we could with the derivative. And we've been doing that for a while, so it seems almost silly to write it down. But we can do that. So let's do some of the harder ones. Okay, so this is like my 5th example. What if I have 4, oh, this one isn't that hard, e to the x plus 3x to the 4th dx. So if I have something like that, I can take the antiderivative of this one and then the antiderivative of this one. That's what this rule allows me to do. So then I'm going to know that the 4 just kind of stays. I could pull the 4 out if it was part of this one too, but it's not. So this one here, I could think of as 4 e to the x, because the derivative and antiderivative both ways are e to the x. And then we would have plus, what would this one become? Well, you keep the 3, x, add 1, dividing by that same number, plus c. So I mean, it's silly to, not silly, we have to write down that rule, but it's something we've been doing for a while with the derivative, so it seems like we should know that. Let's do one with this natural log. We haven't done any of those yet. So what if we have 2 over x dx, something like that, okay? Then we know we could pull the 2 out front, or we're going to keep the 2. If we brought this up and we had that -1, if we add 1, it's going to become the 0, so we can't do that. So we're going to use the natural log with the 2 pulled out front. It's going to be the natural log of the absolute value of that x, that denominator, plus c. Okay, so if you have an x in the denominator, it has to become that natural log of that one. All right, so let's say we have something like, I'm almost out of room on my paper here, the integral of 4 plus u over u du. So I can change my letter. Okay, what if I have something like this? Well, I don't know a product rule, or excuse me, a quotient rule for antiderivatives yet. It's coming. We'll have rules just like we did derivatives. But for what we could do here is we could actually break it up. We can take that u and divide it into the 4 and the u, and then we're able to do the antiderivative. So this becomes 4 over u plus u over u du. So really that's going to become a 1. So when we go to do the antiderivative of that, 4 over u is going to become, can't have that -1 because it becomes a 0. So that part would become 4 natural log of the absolute value of u plus, what does the 1 become? It's u over u is 1. Well, if you have a number, you just add, it was the x, you add the letter. So it's going to become just u plus c. Okay, so I can break it up. Let's see here. What if I could use different notation too. I'm going to use different notation. Okay, so I've given you a couple pieces of information on this one. I've given you the derivative, and I said the original at 4 equals 45. That will help me with finding the C. So we don't know what C is on a lot of them unless we're given a point. Then we can calculate the C. So first thing I got to do is find the function so I can use the function to get that C. So the directions will then probably say what was the original function. Excuse my yawning today. I feel sleepy. So I am going to take this just like we have been and write it up top with an exponent. So our derivative is going to then be 8x to the negative 1/2. I want to bring it up and write it as an exponent. Then we know this is going to become adding 1 to the negative 1/2, which will give us 1/2. So negative 1 plus 1 is 1/2, positive. So then this is going to become, I'm going to have to write it as the function like this, because you can't write equals because then you're saying the derivative equals that, which it doesn't. So the original is going to be 8 times x to the 1/2 divided by 1/2. Okay, so we added 1, which made it 1/2. Then we have to divide by that 1/2. So then this is going to equal 8 divided by 1/2 is 16 x to the 1/2. Okay, which is the same. Oops, I forgot the plus c on there, but that's okay. We'll get it in a sec. Plus c, which is the same as 16 square root x plus c. Both of those are the same. My math lab will take either one. It doesn't mind. Okay. Now I have this information, which will help me find my C. Here's my function. If I put the number 4 here, then I get out 45. So let's write that formula. I would have 45, the Y, equals our 16 square root x plus C. Oops, not x. What do we want to put in for x? The 4. So we can find our C value. So I put it in for X and Y, and then I'm going to find my C. So the square root of 4 is 2. 2 times 16 is 32. So I have 45 equals 32 plus C. Subtract that over, and I get 13. So and when I'm finally done, I then know that the function is 16 square root of x plus 13. So you can find that C by that x and y, that sample point. Okay. One thing I want to make sure you know also is just in notation, if I have d dx, the derivative of an antiderivative, it's going to just equal that function. I think they gave you a couple like that in the homework. Just know that if I'm going to take the derivative, symbol of derivative, of an antiderivative, they undo each other. Okay? So that, I think that came up on one of the problems. All right, let's do a business application. Last question here. What if I say the average cost derivative is equal to negative 1600 over x squared? And then I have a sample too. This will help. That's like our point. So we're given the average cost and we're given the derivative, right? So what is the average cost function? All right, so right now we have the derivative of it. So we want to find the average cost function. Okay, so what we're going to do is I'm going to write this x squared up. So we know we're doing the integral of the negative 1600, but I want to bring this up like this so that we can kind of see it a little bit prettier. And then when we go to solve this, we're going to add the 1, and I'm going to add the 1. That's going to become negative 1600 x to the negative 1, negative 2 plus 1, and then I have to divide it back by that negative 1. So I'm at 1600 over x plus c. Okay, so the negatives cancel, the x, you can leave it as x to the negative 1, that's fine, but, or you could bring it down. So my negatives cancel, this one comes down. Okay, so now we have this information of the y is 100 when the x is 23. So we're going to use this information here for our cost function. So this is our average cost function. Average cost is going to equal the 1600 over x plus c. And now we know this, so I'm going to do 100 equals 1600 divided by 23 plus c. And so I can solve this. I'm going to cheat and use my calculator. So 23 times 100, 100 times 23 is 2300. And then I'm going to divide it by the 1600. So I'm not showing these steps, I'm just saying them. I get a decimal. How did they get? Oh, shoot. I put the 23 and 100 in the wrong places. You probably already noticed that. Hello, X, Y. Whoop, boop, boop, boo. Sometimes I need more coffee before I make my videos. It is early this morning. Okay, so we're here. Let's try that again. I was like, man, that's ugly. We get a decimal. So 23 times 100 is 2300, and then divide that by 16. And I didn't change those, did I? Did I write them back in the same? X is 100. Why did I get such a pretty number when I did it? I got, 2300, 16. I still get the wrong answer. I don't know how I got 7 in all my notes. 23 times 100, 2300 divided by 16. You know, I can do it over and over and over. I still get a decimal. X is 100. I didn't mess anything else up, did I? Hope not. Excuse me. All right. Everyone's probably like, oh, she's got the corona. I don't. I just sneezed. Okay. So I'm not sure where I went wrong. So I'm just going to finish the problem with 1.4375 is my C value. Yeah, I can do it 100 times, but I'm still getting 1.43. I wonder where I got 7. I don't know. Okay. Maybe you got 7 and I just messed up somewhere else. Who knows? So the 23, I'm staring at it like, woo, boo, 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 boo. So the cost equals 23, 100. Anyway, so we have this. So our function for the average cost is going to be 1600 divided by x plus 1.4375. All right, so we have that. And from here, we could actually be asked then, what's the cost? What is the regular cost function? So how did we find the average cost function? We divided by x, right? So if we can times by x, and that would give us the cost function. Okay, so we can go back, we divided by x to get this, and we could go back, we found the average cost function, but we could also find the cost function by timesing by x. So the cost function is going to be 1600 because the x's cancel plus 1.4375x. So we've gone back to even the cost function. All right, so we can use that as well. And our fixed cost would be 1,600. Our variable cost, or our slope, is 1.4375. All right, so those are the examples. There are still more problems. Oh, I'm going to show you this real quick. There are still more examples, in the book as well that I posted for you, and there's still the PowerPoint. One thing I want you to know is if the graphs of three antiderivatives are vertical translations of each other, then they are antiderivatives. So vertical translation, so this means you go up or down. So these could be antiderivatives of each other. This one can't because it's a horizontal, not vertical. This one could. These are antiderivatives of each other. So that might be the cost, average cost, and the derivative of the average cost, or however we want to think about it. All right. That is all I got for you for today.